meter. I think that's February 19 on the Wednesday in class. And also we will post the homework 2 probably tomorrow. And the homework 2 we will do before the first midterm. And also I think we will post some practice exam from the past semesters for you to practice before the first midterm. And I think that's it. So today we are going to first have a recap of the last lecture. And in the last lecture we talked about diffusion, which is one of the mechanisms to, let's say, move the carriers in the semiconductor. And diffusion is different from drift. Drift happens when you have the electric field. But diffusion happens here when you have the different concentrations of the carriers. For example, in this case, the electrons will drift from the left to the right because you have higher concentration or density of the electrons to the left. And the diffusion current is proportional to the gradient of the density. And then here you have different slope of your gradient, different slope of your electron density. Then you have different gradients. Then you have different currents. Here the higher slope is larger current. So if you consider both drift and diffusion, then you have a speedy model to describe all the current components in the semiconductor. And here we have one example to show the energy band diagram when you have the external voltage bias. For example, if you apply 27 volts with the N-type silicon, then the band will be tilted like this way. And here we have very important conclusion, saying that applying positive voltage to the semiconductor, that means you are going to push down the energy band. For example, in this case, we will apply 0.7 volts to the left terminal. That means to the left hand side here, we are going to push down the energy band by 0.7 electron volts. So now you will see a slope in this energy band. And we also discussed that the slope means electric field. So if you have the slope, that means you have electric field. And one more conclusion from here is that for the electrons in the conduction band, so we make an energy there. Electrons are like water. They try to fall down here to lower potential. So electrons tend to fall down. And similarly, the holes, like bubble, they try to move up. So this is the conclusions we draw here in this energy band diagram. 3 points. The positive voltage push down the band. Second, the slope of the band means the electric field. And third, electron will fall down, and then the holes will move up. So we have another example.
The slope of the electric field, the slope of the energy,
yes,
gives you the electric field.
Yes.
But it's 1 over q.
Right? Yeah, 1 over q, yes.
So 1 over q times the slope.
Yeah, yes. Because the energy band, you take that derivative, you will, let's say, because you have the voltage in between, you have the electric field times this q, you get the voltage, and then voltage, you have that, q times the voltage, you get the energy. Yeah. So we have another example here with this non-uniform doping. And this is without external voltage bias. So that means this is in the equilibrium state. We call it equilibrium state when you don't have the external voltage. And in this case, you have higher doping density to the left, lower doping density to the right. So then due to this non-uniform doping, then you will have the diffusion of the electrons from the left to the right. But when you look at the energy band diagram here, this is also an important concept. Equilibrium state means that we only have a single Fermi level. The EF is flat. But due to the different doping, we have different distance from the EF to the conduction band edge, EC. So here we have this slope, and we just said from the previous slide, the slope means the electric field. So you have an electric field, then the electron will drift. So then here you have the electron drift from the right to the left, because as we just said, electrons tend to fall down. So those drift and diffusion electrons will cancel each other, and your net current is zero. This is as expected because your external voltage is zero. So with this drift and diffusion relationship, you can derive the Einstein relationship, because the drift and diffusion cancel each other. Essentially, you will get the diffusion constant proportional to the mobility. And here you have the thermal energy. So this is because the drift and diffusion will cancel each other. Alright, so this is the last lecture. And also we started our discussions on the p-n junction. So we first discussed the MOS structure and the MOSFET. And we say this is a switch. So here the gate terminal, you control the voltage here, then you are going to control the current flow from the drain to the source. So it's like a switch. And if you look at the MOSFET structure, for example, this is N-type MOSFET. The substrate or the body is P-type. And then we have the source and the drain, N-type, heavily doped. So here from the body to the source, we have this p-n junction. And from the body to the drain, we also have a p-n junction. So today we are going to discuss the p-n junctions in more details before we talk about the MOSFET structure later. Alright, so let's start today's discussion. p-n junction, okay. So this is when you dope the silicon with p-type and n-type adjacent to each other. You can define two regions. For example, the left-hand side, you dope with p-type, and then the right-hand side, you dope with n-type. And essentially, you can make this as a two-terminal device if you have a contact to the left and contact to the right. So it's like two-terminal device. And the circuit symbol for the p-n junction is a diode. And it's something like this. You have a triangle. And this triangle is pointing to the right. This is p-type, this is n-type. Because later you will see that the current will flow from the p-type to the n-type. You will have large current. And then the reverse current will be very small. So this is the circuit symbol for the p-n junction. And then you can have the positive voltage and negative voltage this way. And this voltage, for example, you have the applied voltage VA, and then the current across the p-n junction I. So in this slide, we show this current versus voltage relationship, or this IV characteristic, with something as shown in this figure. Current versus applied voltage. Of course, as at zero voltage, zero current, this is equilibrium state. And then when you have positive voltage, okay, so here we need to make some references here. So we can always assume, let's say, that n-type is ground. This side is ground, GND. And then we apply the voltage to the p-type. So, of course, you can assume the p-type is ground, and then you apply voltage to the n-type. Doesn't matter because the voltage, positive and negative, is relative to your reference. So you apply positive voltage to the p-type, similarly as you apply negative voltage to the n-type. But let's make it consistent through the discussions in this class. So we assume the n-type is ground. You only apply voltage to the p-type. Okay. Now, if the applied voltage to the p-type is positive, you will have a large current flow, and here the current actually exponentially increase with applied voltage. So this is exponential function. And if you reverse, this is for the forward bias. Okay, when the VA is larger than 0, and then the reverse bias is when the VA smaller than 0, negative. So then the current will flow from the n-type to the p-type. You are going to reverse the current because you reverse the voltage. But you will see that the reverse current is very small, and it will saturate at this constant level. And then we give this constant level current like I0 because it's negative current, so it has a negative sign here. And if you write the equation for this IV relationship, you will get the current flowing through the PN junction equals to this I0, which is a constant, or more like a coefficient, and then multiplied by the exponential. VA is your applied voltage to the P side, divided by this Vref, and Vref is KT over Q in the thermal energy. Thermal voltage.
What is VF?
It's just a symbol, let's say, KT over Q.
This is a symbol.
Yeah, just use that symbol. Thermal voltage. Because it equals to KT over Q. So this is just a thermal voltage. So it's your applied voltage divided by the Vref, which is thermal voltage, and then minus 1. And you will see that when the VA is very large, much larger than your KT over Q, and you know KT over Q is like 0.26, also from 0 to 6, 26 millivolts. This is at room temperature. We have seen this before. So if your VA is much larger than this 26 millivolts, 26 millivolts, then the exponential function will explode, and then this means it's a very large number. You can ignore this minus 1. So roughly your current will equals to I0 exponential your high voltage Q VA over KT. And then if you look at the negative VA, if you apply negative voltage, then this will become 0 because exponential, let's say the negative infinity, then will be 0. So this term will be 0. It's just you just have the negative minus 1 here. So that means you're going to get this negative I0.
So is it a saturation current?
This is saturation current. So this saturation current is very small, and then it's more like this PN junction is a one-directional device, only allows the current flow from the P side to the N side if you have positive voltage on the P side. So in the integrated circuits, this PN diode is typically used to rectify your current if you want to have one direction current flow. So any questions here? Now we are going to discuss in more details in the next few slides why the IV relationship looks like this. Okay, right now this is just the conclusion for the IV, and next we are going to discuss from the bound model and band model point of view why it's like this. So let's look at the bound model. So you know this dopant in the silicon is going to introduce the additional electron or hole. So here we draw this p-n junction, and this side you have p-type doping. For example, you have boron. Then this boron will give you additional hole. Here this plus sign is a hole. And then this circle with the reactive center, that is your boron ion, right? Because when you give a hole, then the boron will be electrically charged. You give a positive hole, and then which this hole can move, but then what is left to the nuclei of the boron is a charged boron ion, which cannot move. And similarly, to the N side, if you dope, right, then this circle means your dopant, like arsenic, and you have a positive charge center. And then you give additional electron, which is this negative sign here. So you have this kind of physical picture here. Now, because those two regions interface with each other, that means the electron and hole are very close to each other. So can you guess what will happen? Can you guess what will happen here? You see here, this p-type doping give you hole, and n-type doping give you electron. Then what will happen? They are close to each other. Yes? They will recombine. We use the name like recombination, recombine. Basically, they will disappear, vanish. Because the hole, you know, is a vacancy of electron. If you have electron there, that means that vacancy is gone. So then they will recombine. And after recombine, you will see this animation. Okay, I will play it. Please watch this. So they will recombine. Okay, and what is left is this charge center from the dopants, which cannot move. Because electron and hole can move, and they can come together and then recombine. But then here this arsenic or boron ion will not move. So then you will have this kind of recombination. Right. And then we give a name in this region. This is like a depletion. Because there's no movable free electron or hole. It's like depleted. We give a name to this region, called depletion region. But then this depletion region typically is within a short distance. Okay. Once you have more and more recombination going on, eventually here you will not have more recombination. Why is that?
Too far.
Too far, right? So that's too far away. That's too far away. So then you don't have the recombination. So that means there is a boundary here, and we give a name that is the depletion width here. You see, this is a WP, is a depletion width for the P type, and WN is the depletion width for the N type. So then this is a transition region from the P type to the N type, and we call this depletion. This depletion, P type depletion, N type depletion. So any questions?
So there will be electric field.
So by the way, we are talking about the equilibrium state here. The external voltage is 0. Okay. So without external voltage, this is what happens. This is what happens in this junction.
So would diffusion take place first? Because like there is a lot of electrons on the n side. There is almost nothing on the p in the beginning.
So
there will be diffusion.
So we will go to that point very shortly. Yeah. Just stay tuned. We will talk about this in the next few slides. To talk about this, we need to look at the band diagram. So that's why I prefer to use this band diagram to describe the process. So this is a band, and you have done this homework. So if you have the p-type silicon, then you will have this kind of band diagram. So where you have the EC and EV, and then the Fermi level, for p-type is close to the valence band, EV. And on the right, you have n-type. So the Fermi level, EFN, is close to the EC. Okay. But right now, when we have those two band diagram, we assume that you have two separate silicon. One is p-type and one is n-type. But now this pin junction means you will contact those two silicon together, right? So they will interface with each other. Then something will happen. So we still start with the equilibrium state. That means the external voltage is 0 here. External voltage is 0. Equilibrium state. Okay. And recall what we reviewed at the very beginning of today's class. We said that at equilibrium in the semiconductor, there is only a single Fermi level. Or Fermi level EF is flat. Or here it says Fermi level will run up. So what does this mean here? So you say the EFP and EFN, right? And they are different. So now they need to run up. Okay. Let's still assume the references to the n-type. So here, this is your ground. Okay. Let's assume the references to the n-type. This is ground. That means we assume the n-type energy band will not move. Okay, will stay there. So then you need to land up. So here, this is the difference. That means your EFP is to move up by this difference. And then you can have a single Fermi level in this system. So look at this animation, okay? You see the Fermi level will land up, but then the EC-EV for the p-type will move up. Now, what will happen? Here are the EC and EV in the middle. This is the depletion region, actually, we talked about earlier. So the EC is still continuous. So you need to draw them like this. The EC will collect from the p-type to the n-type following that slope. But the EF is a single level. Any questions?